Thank you all for joining our latest webinar. Today we're going to talk about smarter fastener and hole measurement automated with GelSight. I'm Abby Lindberg. I lead GelSight Applications Engineering team. And just a couple items before we get started. One's just a reminder, we're going to be recording this session and it'll go up on YouTube after this, so you can watch after the fact. And we also have Q&A throughout. So Frank Chang from my team will be on the Q&A answering questions live. And we'll answer some Q&A at the end as well. I know this might be tricky to find in Teams, so you might have to click on the top bar and click, a button to get to the Q&A section. The chat is disabled, but Q&A should be enabled. So with that, we also have Dennis Lang joining us, and I'll hand it over to Dennis to introduce himself and kick off the webinar.
Yeah, good morning and good afternoon, depending on where you are in the world. Thank you for taking your time to join us today on this topic, hole and fastener measurements. We are going to kind of be combining them. So people use GelSight both to look at holes that are for fasteners and actually for holes that aren't for fasteners. Some examples of that could be the end of a pitot tube or the end of a needle or a different kind of medical device. So we are going to be kind of combining, and GelSight does a lot of work with aerospace, so it's a little bit aerospace centric, but of course it applies across. So if we think of the fastener hole system, obviously this is a super critical joint in many different kinds of systems and sophisticated, whether it's aircraft, spacecraft, or a different kind of power generation, infrastructure with pipelines, things like that. And of course, the fastener hole system transfers critical loads across joints. And given these are critical loads, oftentimes with many cycles over their lifetime, getting the hole measured properly, the fastener flushness, all of these things down to the micron is something GelSight can do, whether we're in the lab or the fields. It's a pretty unique capability. We detect the gaps in the mating surface issues and protrusions that the typical tools will miss. And in addition to that, we output a 3D map where the fastener actually seats. So this is great. We can definitely start to help people predict load imbalance or fatigue based on the hole, whether it's new production or in a sustainment or MRO application. Surface finish and edge quality, of course, are super important to fatigue life. When we think about things moving over the course of millions of cycles, all kinds of deleterious effects can be happening around that. So we can be creating cutting, we can be creating stress risers. We could have problems in the countersink that you might not have caught if you don't use a tool like GelSight. Of course, moisture traps lead to corrosion, and this is something GelSight spends a lot of time looking at in the field. Corrosion of all different kinds, but certainly corrosion in and around the fastener. When we think of fasteners that have been recessed too deeply, they have sealing defects, and then you start putting these into scenarios where you have dissimilar material sets, that galvanic corrosion can lead to very problematic things that aren't expected within the design parameters of the system. And of course, in more modern times, when we start looking at mixing composites and metallic substructures, say a composite skin with a metallic stringers, you can have even more problems. And certainly there have been some famous examples of aerospace systems that have had challenges based on that. Of course, getting your first pass assembly, being confident in what's going on, and real-time feedback. So you know if your drillings are right, if your finishing processes are getting where you need to be. Very important when you think of drilled holes and also rivet quality. We have scenarios where the first application of GelSight in a new company was actually looking at rivets that were being damaged going through the feeder, and they were finding damaged rivets in the holes, and they had to trace that problem back with GelSight to the rivets coming through the feeder were being damaged, so they were able to trace down where that was. And then finally, one of the really unique things about GelSight is we give you traceable, visible proof of conformance. either through our one-touch PDF, which has kind of been the standard modality of GelSight over many years, or more recent developments as we've been moving more into production and automated environments where we have increasingly rich APIs that output that data. So GelSight really gives inspectors and engineers eyes where they couldn't see before. And that's really a great way to think about GelSight as we go through what we see here today with Abby on how you can apply this into your applications.
Thanks, Dennis. So I think I'll jump in right to the live demo, and we'll start with a little how GelSight works, a little overview of that. So I'm holding our GelSight Mobile Series 2 system here. We've got one button on it. And when I click that button, I'm taking 6 images, one with each one of these banks illuminated. So I'll actually pull up a slide to kind of illustrate what's going on there. But basically, we take those 6 images with the 6 different lighting orientations and do a series of slope calculations based on pixel intensity to give us a normal map and a 3D height map from that. So in conjunction with the camera, lens, and illumination system, we have a gel sensor. And this is what lets us look at surfaces regardless of optical properties. So, glass, metal, textile, all looks the same to the GelSight system. We don't have to do any kind of settings changes. We're looking at everything through that pigment layer, which I know we've highlighted in some of the other webinars that we've done. So I'll put this gel back into the probe here. And we'll jump over to the GelSight mobile software. So let me share that over here. Get that started. And we'll go live here. And the first thing that I'm going to do is actually just press my fingertip into this to give you an idea of the resolution. So you can see my fingerprint showing up there. So now we've got a couple examples that we'll go through for this webinar. I've got a bunch of standards sitting here on the desk. I'll hold the first one up, but we're going to look at this bolt hole standard, and we'll take a look at one of these large holes, and we'll walk through our hole diameter function and some analyses that go with that. And then we'll get into fastener flushness too. So let me go ahead and put this back on the desk here and switch my camera so you can see me take the scan. But the first scan we'll take is just going to be of one of these holes here. Just going to press the probe down onto the surface like that and click the button to take the scan. The 3D data generates now, and once that's available, we can open that up and do some analysis. So here's the scan that we're looking at, and I'm just going to click 3D. And then we'll be able to see the 3D reconstruction of that hole. So here's that. We could export this as an STL file from here as well, but I'll jump back over and let's talk about the hole diameter function. This works in a couple of ways. The first way that we'll go over is a manual method. I'm just going to click hole diameter here to add it to my analysis. And for this, I'm just going to click on the screen and draw a hole approximately the size of the one I'm looking for and click Analyze. And you can see the diameter actually snapped to the edge of that hole. And we're outputting the diameter and the circularity, so how out of round this hole is. And from this, we can just turn this into a PDF report. We'll just click PDF in the corner here. And now we can attach this report to whatever kind of system we're handing this in with to show what analysis we've done. So this is an example of a good hole diameter measurement, but a lot of the time so we're going to be interested in hole quality, whether a hole is out of round or maybe a snowman hole. And let's take a look at an example of that. So I'll actually go back to capture here. And for this, I have a couple holes drilled in some acrylic, kind of another highlight of different materials that GelSight can look at. And I'll take a look at maybe this hole on here. So you can see not the nicest hole. And I'll take that scan and we'll be able to open that up and do some analysis. Maybe we want to measure how out of round this specific one is. So I'll come in here and I'll do the same type of manual measurement. I'll add our hole diameter function. I'll draw a shape here. I'm just using the touchscreen, really nice use case for the touchscreen with our analysis functions. Quick little line to draw. And maybe what I'm interested in for this application is actually this distance. Maybe I want to measure, how far out of round this is on this worst scenario. You can really see where the hole deviates from that round, just visually with this overlay. So for this, I'll go in and I'll add a ruler and we'll just measure that. We'll snap to the edge of that circle there. And maybe we'll even add a label to this so that when we export our data, we can reference the dimension on the overlay as well. So another example of issues that we see with holes are just defects on the edges of holes. And that can be something that's challenging to measure with other systems, especially with getting the depth of field right for that. So for that example, I have another sample here. We'll look at this, just visually, it looks fine, but when we take a scan, you'll see a pretty big defect right on the edge of that hole. And I'll take a scan here, and you can see that defect right there. So that's what we'll go in and we'll measure. So I'll open this up and we'll zoom in here, and I'll go ahead and use our offset function, which we've gone over before. But offset's basically just going to be a Z height measurement. I'm going to draw a line across my defect along the edge here. And we can see that profile come up. And here I'll go ahead and just add 2 reference surfaces to configure my function here. And I'll say I want the minimum point to give me the deepest point. So I can see that the depth of that defect on the edge of this hole is about 120 micron. I know, Dennis, you had an application recently where you were looking at damage on the edges of holes, if you wanted to talk about that.
Yeah, there's a really interesting application I can share with people, and it's unfortunately in some cases not a very uncommon story with GelSight when we come into scenarios where previously kind of legacy inspection methods or maybe just visual inspection was happening. But holes that kind of look like this in the field is the end of a pitot tube. And when an aircraft comes in, even a new aircraft, actually, if it has a pitot tube mounted, these are, you don't want to remove these, and certainly in MRO, they're not typically removed. But a pitot tube has a chamfered end like this, and if it's been flying, of course, it's sustaining damage from, various kinds of debris that are in the air, so airborne particulates, bugs, different things are hitting it. Potentially some, a handler accidentally hits it. But in addition to that, there's just the manufacturing tolerances that are there. And these are something that are historically very hard to measure. It wouldn't be hard to measure if it wasn't attached to an airplane. But you saw how easy. I saw someone's reaction. That's a very typical, and it's fun for us when we demo GelSight to see people surprised. So we're able to measure things on pitot tubes to a level of precision that really was not happening before. And in the case of one company, they were receiving pitot tubes significantly outside of spec on the data sheet that their vendor was providing with the product. So they called the vendor up, and the vendor said, no, they're good. And they said, well, here's the GelSight PDF reports showing you they're not good. And of course, pitot tube is a very serious safety of flight component. And that particular situation really caught that they were being manufactured out of tolerance from the OEM of the pitot tubes being installed on aircraft, and those aircraft were being put out into the world. So going back and getting that fixed, the supplier, of course, had to go back and check what was going on. And once they did that, of course, flight becomes safer when you have things like that. So really interesting story where the fact you're able to get a measurement like this in seconds, you're using GelSight for other things on the aircraft, led to an improvement in the safety of flight.
Thanks, Dennis. Yeah, I like that story. So I think so we've gone over some defects on the edges of holes and that application example. But now let's jump into just measuring diameters and really how we can automate this analysis in the GelSight mobile software. So I'll head back to Capture here, and we're going to take a look at this reference standard that I have that has a bunch of holes on it that are approximately 1 millimeter in diameter. And we'll take a couple scans of that. So I'm going to go ahead and scan this first one here. And it'll generate the 3D. And then we'll go and configure that for automated analysis. So let's open this one up. So far, what I've been doing is drawing a diameter, like drawing the hole on the screen and then clicking Analyze, but we can also configure this to run based on a nominal diameter. So I'll click the hole diameter function, and I'm actually going to open up the pencil icon for advanced settings here. And I'm going to enter 1 millimeter. And I'll click Analyze. And it's going to search our entire field of view for a hole approximately 1 millimeter in diameter. So you can see it just found that without me drawing the shape, just based on my nominal diameter being entered. So if I'm happy with my configuration here, I can click Set Defaults. And now this is going to be how that function is configured going forward. In this case, maybe I want to make a dedicated function to specifically measure holes around 1 millimeter in diameter. So to do that in our software, I'm going to go to Configure, and then we'll go to Analysis here. We'll find our hole diameter function on our list, and we have this option for New Variant. So doing this clones a function. So maybe I'll make one specific to 1 millimeter hole diameter. And now I've added that to my analysis tool. So maybe I would have one that's 1 millimeter, one that's 5 millimeter, if there were two kind of sets of hole diameters I was interested in. This is also where I could configure pass-fail criteria based on my application tolerances. So we'll jump back over to Capture, actually. And now that I've configured my analysis, I can actually run this as a routine from the Capture page instead of having to click Analyze and configure the analysis every single time. So I've got Run a Routine here, and there's my 1 millimeter hole diameter function. I'll go ahead and select that. And now if I scan one of these other holes, approximately the same diameter, we'll take a look at this one maybe. It's going to generate the 3D data here, and then it's going to, you'll see it'll say analyzing 1 millimeter hole diameter. So now the analysis is performed. I've got a green box showing me that it's completed and passing. It'd be a red box if it had failed. And then I could open that up and we can take a look at that analysis. So you can see it located this diameter, and there's our information for that. And we can also take all of this data and export it to a CSV file. So if we jump over to Explore, you can see here's a bunch of other hole diameters and fasteners that we've measured previously. But if I wanted all of this data into Excel or some other program you wanted to put a CSV file in, I could highlight all of these and select Export CSV and customize the report that I'm interested in. So maybe scan name, the gel serial number, the creation date, and maybe I'm going to export hole diameter and just diameter, or maybe I want circularity as well. And click Generate CSV to turn that into your export file. So the first thing we've automated was basically the hole diameter function, but now we can talk about fasteners, which would be like the next step in this for a lot of applications. So what I've got for that, we have a fastener plate here that we'll take some scans of. We'll hold this up here to the camera. We can see there's several fasteners, and we'll take a couple scans of these. We've got one fastener that's pretty flush to the surface and another one that's protruding to give you an example of a passing or failing configuration. So let's jump back over to Capture here. And I'll actually enable one feature on this page too that can really help with fastener and hole measurement. We have an option for a guide. Maybe I want to put large circle or small circle. This is just a visual indicator. It can help the operator really line up the GelSight mobile handheld probe to get the fastener or the hole in the center of the field of view. It's just a visual indicator that can be helpful for usability. So for this, I'll take a scan of the first fastener on this plate. I'm going to put it in the center of the field of view here. And it's going to generate my 3D data. And we'll open that scan up. So now we'll talk about our fastener algorithm. Actually, I guess first we'll click on the 3D so we can take a look at the 3D here. You can see this fastener pretty flush to the surface here. And we'll jump back over. So I'm going to select fastener. This is our generic fastener function. And I'm going to click on the pencil icon. This is going to be where I can configure my parameters for each fastener type I'm going to be inspecting. So the first input is the diameter. I know this is approximately 7 millimeters, so I'll leave that. But let's say you had multiple diameters of fasteners you would be inspecting. We would just create variants like we just did with that hole diameter function. So you could have one for different fastener types. The next category, the next input here is the flushness offset. This is how far inside the outer diameter of the fastener we're going to be checking the flushness. It's basically going to create a ring inside the fastener where we're going to look to see how flush it is with the reference surface. And then we have our pass-fail criteria here. So it can't be, inset more than 100 micron or protrude more than 100 micron. And then we have our reference surface distance and width, which is basically defining a donut shape around our fastener where we're going to be checking the flushness with respect to. Being able to configure that is pretty key to this application. And it's also able to handle curved surfaces in addition to flat surfaces. So fasteners on curved surfaces won't be a problem for the system. So with these configured, I'll just go ahead and click Analyze here. And you can see the output. We've got our flushness min and max. Those are these blue dots and red dot respectively. So the blue dot is the deepest point along the fastener, and the red dot is the tallest point along the fastener. You can see, so it's inset about 80 micron, and then the tallest point is still like about 5 micron into, like below the reference surface. And then we've got the head dishing that's being reported. So if your fastener has a curvature to it, or that maybe that was applied from how it was installed, you'll get that calculation as well. And then perpendicularity. So you'll see if your fastener was installed at an angle with respect to the reference surface too. So we showed from the capture page how we can take that scan and run it as a routine. But we also have another option for automation, and that's going to be running this with operator mode. So I'll actually go over to operator mode here. And operator mode is a locked out interface. I'll delete this so we can talk about it. It's basically a locked out interface in the GelSight mobile software. So if you're going to be using GelSight to only do a singular task, you can configure it to be the only thing available in the software. So we can enter a password protect it, so that you have to enter this password to exit operator mode to access the rest of the software again. And we can also decide where our scan data is being saved and whether or not we want operators to be able to calibrate or validate. So there are plenty of scenarios where we might want operators to just be taking the scans and somebody else to be doing the actual calibrations. So you can configure if you want that to be allowed from the operator mode or not. And then we can select what routine we're going to run. So in this case, I'm going to select fastener. I can see that I'm going to be measuring the flushness of a fastener rivet, and I have pass-fail criteria defined. We'll also be able to generate a CSV with all of this data once we exit operator mode too. So like the end of the shift, you could generate your report for that day's worth of fastener inspections. So I'll go ahead and I'll enter a password here, and we'll click start to take a look at what that interface looks like. So you can see it's a much more simplified version. We're basically seeing the live image here, and you see the scan history. So I'll go ahead and I'll take a scan of that fastener again. Take this scan here. And it's going to create the scan, generate the 3D data, and perform the analysis for the fastener again. So we can see that result there. And I can click redo scan or next scan. I can't do any of the configuration. All I can do is select an option here. So I'll click next scan. And now we'll scan an example of one of the fasteners that's protruding. So I'll take a scan of one of the other ones here. And we'll wait for that result and take a look at that. Analyzing fastener, and we can see the overlay gives us a nice visual indicator already that this is a failing fastener. It's protruding about 150 micron. We know that was out of our 100 micron tolerance. And you can see part of the fastener is within spec. You can see the green, and part of it's out of spec, which is the red area. And then to exit, we need to enter our password again. But maybe Dennis, could you talk a little bit more about how this can help you go from the lab environment to production environment?
Yeah, it's really been a great journey GelSight has been able to go on with our customers. GelSight really started in the lab. Our origin story is a spin out of the MIT robotics lab. And we really built our first products for lab environments where we were building benchtop systems to help people. So it's kind of the lab curiosity kind of level of development where people had interesting problems they could take to the lab and were able to see things they had never been able to see before using GelSight. While using these tools, they started to notice they were capturing data that was just absolutely critical and so much more rich than what they were getting with their legacy inspection methods. So if you're using things like a pin gauge or a set of calipers or even trained visual inspections, many things can be missed, of course. You can miss small surface flaws. Repeatability is obviously extremely difficult in Industry 1.0. That's why we've all been on this journey to Industry 4.0. Things like fatigue cracks, improper flushness, poor fit and quality, these things we're still getting through. When you look at a fastener flushness, of course, determining where you are on the surface, in some cases, the tool sets, it's extremely dependent on where you set it. GelSight uses the whole surface and creates the normal plane. Once some of these things were starting to be noticed in the lab, it really started to deliver what others couldn't, and people really started to appreciate that. So we're showing burrs, scratches, sealant gaps, micron level mismatches in the fastener holes, around the heads, even on the fasteners themselves. We can measure them all with GelSight, combine them in the same report. As our systems were developed more towards this, we were delivering now mobile systems. We're also delivering systems, software products for our mobile systems that increasingly allowed both mobility and automation. And not only that, it's really the digital data output that promises the long-term improvements if a customer starts partnering with us with this product and these solutions and building this data set. So now the field teams are taking notice. And as the field teams were taking notice, they start asking for features like the ones Abby was just demonstrating, where a manufacturing engineer might want to lock down a function for very repeatable things and control what the user of the system can actually do. So we were bringing those into our software platform and allowing those inspections to be enabled by our very unique hardware that was also being developed in parallel, being robustified, becoming smaller, easier to use. So now we're in the field looking at early stage corrosion when fasteners are removed around joints. Again, we can actually look at the sealants themselves, even if they're clear. That's one of the huge benefits of the gel and GelSight, in addition to not needing those supports and some of those other things. We can confirm the fastener seating in seconds, as you saw here. And then finally, the digital record keeping was one of those kinds of things that really started helping customers not only prove conformance within their organizations, but when they're communicating with partners, whether they're suppliers or customers, they've now got the fast ability to share rich data, pictures of where they actually took it. and show what is actually going on. So given these benefits, we tend to broaden out. GelSights tend to kind of land and expand. There's one system that goes in, people start saying, "Hey, I want to borrow that," and next thing you know, they're going into other places. And today, we're on the factory floor measuring holes, fasteners. We're measuring fasteners installed, whether they're painted or not. We're measuring holes after fasteners are removed to see if there's damage under there. We are looking at joints and pipelines and corrosions in pipelines, planarity. So we're looking at surface finish and some of those kinds of things. And it's really offered a repeatable quantitative method to meet the various specifications you guys all need to meet here today. And it's really led to kind of some breakthroughs. A final thing that I'll talk about when we talk about the production environment and the sustainment environment is composites. Composite holes obviously often are not as clean, especially in a sustainment or an MRO, so a composite hole that's been in service. And damage kind of presents differently. So the surface of a composite, if there's no paint on it, can actually be sort of clear. And then you have matte underneath. In the case of, say, an aircraft skin, you might have an ESD layer for electrostatic discharge abatement, whether that's lightning strikes or other things to protect the sensitive electronics on the aircraft. It's very important when you're looking at hole damage in these cases to know what's going on in that hole. And GelSight, as you've seen in these pictures, gives you that imagery. So our customers have been able to make real breakthroughs, whether it's getting paint to adhere or whether it's understanding the damage rework processes are creating, even being able to measure the tooling making the holes. So what GelSight is delivering today is an operator independent inspection process that is also capable of being automated both at the user level, but even further with automations into robots and things like this.
Yeah, and throughout this demo so far, I've actually been running our API demo in the background as well. So let me pull up what that looks like for even further kind of integration. So I've been working this whole time on a tablet over here with the GelSight probe connected to it. I'll stop sharing over there and I'll actually share from my laptop, which has been running a TCP connection through our API demo to the tablet that's actually connected to the GelSight mobile system. So I'll actually jump over to share what that looks like. To show kind of what we can do for custom integration. So this is just our API demo. It's on our GitHub for any GelSight user to work with for integration. But you can see we've actually been logging all of the data that we've taken during this webinar. So we can see we've been saving all of those scans and all of the analyses as well. I could actually request my live view and subscribe to live images from this. And now I could remotely see my live scan. So I can see my finger being pressed into the probe that's connected to a different computer. We can also see flags like the gel state, for example, which will tell us whether or not we're making contact with the surface. So we can see no contact now, but if I press onto the surface, you'll see in contact and then no contact when I let go. So kind of enabling some other options for robotics applications. And this is available for GelSight users to work with, whether it's, integrating with a robot or whether it's just integrating with where you're going to be sending your data. Maybe you just want all of this data to be automatically sent to one of your systems rather than having to manually export a CSV file or a PDF report. So all of that is something that can be configured. So maybe Dennis, you could kind of summarize what we've talked about and maybe the value brought by GelSight.
Yeah, let's get through we'll wrap it up here and get to the Q&A and maybe a little bit of a surprise at the end for those that stay with us. So, really the value of GelSight in plain terms, first and foremost, we make inspections really fast. Those of you that have maybe used a CMM to inspect a hole know how painful that is, how slow that can be. You have to take the part, you have to do all the setup. For us, you can imagine you walk up to the hole in the environment in situ and you make the inspection. So we don't need a stand, we don't need the lab, we don't need the nicely climate controlled environment. We don't need a perfect surface. You just walk up, push the system on there, and capture the image. You're done. 150 milliseconds, you've made your capture. This leads to really high throughput, shorter inspections, less downtime, and it doesn't matter if you're on the line or in the field. Our systems do everything from production on robots to living with field test teams. Our cases fit under the seat in front of you on an airplane, and they go into all kinds of austere environments to bring these lab level measurements there. It's a very simple system to use and increasingly simple. Every time we release new software, which we do about 3 times a year, there's always a focus on automations, on improving things like usability, image stabilization. We're always doing things like this because we want our systems to be simple, faster, and simpler to use. This really captures the trend of needing to have skilled inspection to be repeatable by anybody. So if we have a manufacturing engineer that can set up the process, anybody can run operator mode. I've run MSA in conference rooms with people who just almost can't believe GelSight works. It's by design. It's something we at GelSight are very, very focused on. We've published papers with partners about. Turning that into those simple guided steps with those outputs, of course, reduces training time and ensures consistent, reliable, and documented results that you can go back and audit later. You're getting quantitative decision making. This is really important, especially when you look at the typical ways of inspecting holes that are in situ or on large pieces that can't be either disassembled or taken into a laboratory environment. You're getting hard visual dimensional data. We've proven the consistency, whether you're in the depot level to the metrology lab. We have papers where customers have actually done MSA studies against very expensive desktop kind of standard systems to GelSight, and we match that in the field with our systems. So you can be very confident on your calls about part conditions, and you can present the traceable reports to back that up. I think it's really important to emphasize that you see what others miss. I can't tell you how many times GelSight has seen cracks in interesting places, definitely including around holes, which are obviously a place for both stress risers and cyclic stress where it makes any kind of damage, sometimes much more problematic, of course. GelSight allows you to see that. Even our live view, if you push on the edge of the hole, sometimes you can load it, you'll watch the crack open if you're wondering if it's a crack or a scratch. This is a really unique differentiated proposition GelSight offers in a mobile solution. So around and inside holes being that major risk area, we capture it. The micron level pitting and fretting and edge damage that we can see, there's no guesswork about that. You're able to make the inspections and you're able to tie it to the results. And I think finally, this is something I was talking about, 4 years ago when I first started here, and I don't think it was being appreciated as much as it is today. GelSight's platform was designed to have a digital output. Computer vision images really lend well to both building large data sets and then over time applying AI-driven tool sets to really start to understand your processes better and tie the full product lifecycle together. We today are helping customers feed fatigue and fracture mechanics models so they can make better decisions about the availability of the aircraft or the spacecraft. And as we are creating this data set with these customers who have tens of probes deployed in their fleets, they're really learning the value of that digital data set beyond just the PDF, which of course is extremely valuable, but now the ability to get smarter about your fleet by using GelSight. This is something over time that is very important. And when you start thinking about automating that and having that data-driven quality control in your fleet, it really can bring some amazing benefits to you. So with that, thanks, Abby, for showing what you did. Thanks, everybody, for your attention. Today, I think I see we've had some questions coming in, so we'll give the time to that now.
Yeah, go ahead and enter some questions in the Q&A. Reminder, it might be a little tricky to find in Teams, but I'll go through, and it looks like we have a bunch that have been answered already that I'll read out loud for the group. But one is, does the camera need to be touching the surface of the part? The gel sensor does need to be touching the surface. So you'll see this is the gel on the end. It's pretty soft. It's very non-destructive. I mean, it's basically the hardness of your fingertip. It's kind of a good way to think about it. Be, the equivalent of pushing your finger onto something, be pushing the gel onto the surface. We have another question that said, is GelSight capable of measuring and quantifying surface roughness, and what range of roughness can it measure? And also thank you to Frank, who's been answering these questions throughout. But I'll add something to this one too. So the GelSight Max system will go down to 0.2 micron RA and up, and the Series 2 system that I'm using here today is about 2 micron RA and up. So that's a 80 micro inch for anyone interested in those as the units. See if there are any that haven't been answered yet. We have a question that says, if I had a coating over a fairly rough substrate, say blasted steel or unsanded wood, is there a way to baseline that out so that I don't get false positives for negatives in looking for defects? Yes, depending on what analysis function you're using, it's going to do the reference surface in different ways. But if we were using the pit detection, for example, we would be able to filter out pits that are deeper than or shallower than a certain depth, so we can ignore them. Or it might, depending on the other analysis functions you might be interested in, it might be kind of ignored by averaging of the reference surface as well.
In addition to that, Abby, and this is something we do on wood specifically, but other things. One of Abby's demos actually on wood, but we do it in production and automotive on wood surfaces. And that is, we have an AI toolbox that you can actually train. So you make scans and you're able to either do classifiers or pass fail. So if you think of the back of a consumer product you might hold in your hand that cares a lot about feel, but maybe it's difficult to quantify from a metrology perspective, we can actually go through an AI training and we can classify that to what the industrial designer was intending with that. In the case of wood, you can make sure you're getting the right wood, the right grain, and the right finish. When you think about cast plastic pieces on interior surfaces, that surface texture is very important. So everything can be molded in the right color of plastic, but if you have slightly different texture, they look like they're different colors based on reflections. GelSight captures that. We do that as an application today. So many different ways to handle that, depending on what you're trying to do there, Will.
Yeah, we think that that's probably going to be a good topic for one of our future webinars as well, diving into the AI design function. So I'll answer maybe one or two more questions here. We've got one question that says, how do we know GelSight is steady? We can handle GelSight steady enough for vibration. So the image acquisition on this system happens in about 125 milliseconds. So it happens very quickly to minimize that. But we do also have advanced image alignment algorithms as options for the system as well as the Mac system.
So we do software and hardware. We control for that in many different ways. And we run MSAs that are handheld to make sure we include that across users and assure the system is working, whether it's through the image stabilization. We have gone through many, when we develop systems, we worry about the button a lot because that impacts. So yeah, we definitely think about that quite a bit. Make sure we're a very usable system across user types.
All right, so I see there's still some pending questions. We'll make sure we follow up after the webinar, but we want to thank everybody for staying on here. So we'll pull up one special treat for the group.
Yeah, so this you never know sometimes with marketing, but this teaser has already made a LinkedIn, so it's there as well. But GelSight is a hardware-enabled software platform. So we have a software platform that works now across multiple devices. We add functionality to it about 3 times a year with 3 releases, but we're also able to bring hardware releases. So we went from desktop to a mobile system. Our mobile system, we've added silicone skins and wrist restraints and things like that, so they're more durable in a production environment. But now we have a new system coming that's going to be addressing some things that I believe will be of interest to everybody here. So just a fun little quick teaser. This is not a full product reveal today. I apologize for that. But I think users out there will understand kind of where we're going once you see it. So thanks, everybody. For those that are already existing GelSight customers with NDAs, give us a call. We can start to do some conversations about this product. But we appreciate your time. Thanks so much.
Thank you.